welcome to the chapter on vector spaces. Giuseppe Peano was the first mathematician who formally laid out the axioms of a vector space. He also did some other interesting things, like described the natural numbers with something called the Peano axioms. He invented space-filling curves. There's a picture over here of space-filling curves. And he also tried to create his own language based on Latin, but having no grammar. Now, if you're taking differential equations, or if you plan on taking differential equations in the future, an interesting fact is that solutions to linear homogeneous differential equations form vector spaces. So here are two examples of naturally occurring vector spaces. So let's talk about vector spaces. A vector space is a set of objects called vectors, and the vectors have to obey the 10 axioms that you see in the box here. Now, I'm not going to go through and talk about each one. The real numbers form a vector space, so most of those axioms are going to seem familiar to you. There are a few I do want to point out. Number one is called closed under addition. If you have two vectors in a vector space, their sum still has to be in that vector space. Number 6 is called closed under scalar multiplication. When you take a vector and multiply by a scalar, you have to stay in the vector space. Number 4 says every vector space has to have a zero vector. And number 5 says for a vector in a vector space, there has to be a negative such that when you add it to your vector, you get the zero vector. So let's look at some examples. The most familiar example is Rn, which is the set of column vectors with n entries. Here I have a representation of R3, and I've only given 3 vectors in R3, but of course there are infinitely many. Any vector of this form ABC, where ABC are real numbers, is in R3. So we can see that the zero vector is in R3, the vector 1, 2, 3 is in R3, and the negative of that would be negative 1, negative 2, negative 3. Mn is the set of matrices of size m by n. So m rows, n columns. Under matrix addition and normal matrix scalar multiplication, that is a vector space. So M22 would be the set of 2 by 2 matrices. And again, here I've listed 3 vectors in M22. The third big example that we'll use a lot is P sub n, which is polynomials of degree less than or equal to n, using the usual scalar multiplication and addition. Notice that the n here is a subscript, not a superscript. So for Rn, the n is an exponent, but when you're talking about polynomials, Pn, the n goes downstairs. That's polynomials of degree less than or equal to n. And here I've got a picture of P2, which is the set of polynomials of degree less than or equal to 2. Now, I want to show you why we have degree less than or equal to n and not equal to n. Suppose in my picture here, I take the vector q plus r. Let's add those two vectors together. We get negative t squared plus 3t plus t squared plus t. That's equal to 4t. That's no longer a polynomial of degree 2. So I started with 2 polynomials that were quadratic, and I ended up with a linear. And that's why we want this to be less than or equal to n, so that Pn will be closed under addition. One of the best ways to understand what a vector space is to understand what one isn't. So to do that, we need to talk about subspaces. A subspace of a vector space is, first of all, a subset. So H is a subset of a vector space V, and H has to have 3 properties. The zero vector has to be in H, and H has to be closed under addition and scalar multiplication. And I've written out what those conditions are explicitly for B and C, but this is a definition you definitely need to memorize. 2 things I want to point out. Every subspace is a vector space in its own right. So you've got a big vector space, V, you've got a subspace H. H is a vector space in its own right. It's just a subspace of V. Another comment is that every vector space has at least 2 subspaces, itself and the zero vector space. And when we talk about a proper subspace, we're excluding those 2 extremes. So let's go through and look at some examples. The subset of diagonal 2 by 2 matrices is a subspace of M22, which is the set of all 2 by 2 matrices. And diagonal matrices look like this. They have zeros off the main diagonal. Okay, so let's just verify the 3 conditions. The zero vector is indeed in D. That's a diagonal matrix, so that one checks out. For B and C, we need to give ourselves two generic vectors in D. So a vector in this case is a matrix. So U and V are both diagonal matrices, and alpha is going to be a scalar. That should be a V. U and V are both in D. So for condition B, we need that U plus V should also be a diagonal matrix. Well, let's add U and V together. We get A plus C, 0, 0, B plus D. That's certainly a diagonal matrix. So that one checks out. And then for property C, alpha U should also be diagonal. Well, that's the matrix alpha A, 0, 0, alpha B. That's diagonal. So we've got M22 here, and we've got diagonal matrices that live here. They're closed under scalar multiplication, and they're closed under addition, and the zero vectors in there. Okay, another example, R2 is not a subspace of R3. This is an interesting one. Here's why. R2 is not even a subset of R3. The first condition of being a subspace is you have to be a subset. Here's a vector in R2, AB. That's not even in R3. So it stands no chance of being a subspace. However, there is a copy of R2 that lives in R3, and that's this next example. The set of vectors that look like AB0 is a copy of R2 that lives in R3 because the vectors in H now actually do have 3 entries. And so let's use the definition to show H is a subspace of R3. I've already done condition 1, the 0 vectors in H, no problem there. Condition 2, if I take 2 vectors in H, then their sum should be in H. So U plus V is equal to A plus C, B plus D, 0. Well, that's in H, because the only condition on H is that the last entry has to be 0. All right, and then if C is a scalar and U is in H, then CU is CA, CB, 0. Again, that's in H. Okay, another example. Let H be the unions of quadrants 2 and 4 in the plane. So vectors in H look like this. If you're in quadrant 2 or 4, then the product of your coordinates is going to be less than or equal to 0. So the 0 vectors in H, because 0 times 0 is less than or equal to 0, so that's no problem. We're going to show H is closed under scalar multiplication. So we take a vector U in H, and let C be a scalar. And let's look at U, well, I should say, let's look at CU. Usually we do scalar multiplication on the left. CU is equal to CA, CB. Let's see if that satisfies the condition. CA times CB is equal to C squared AB. Well, that does satisfy the condition. That's less than or equal to 0 because AB is less than or equal to 0. And C squared is either 0 or positive. Unfortunately, H is not closed under scalar multiplication. And to show that, we just need to find 2 specific vectors in H whose sum is not in H. So I took a vector U in quadrant 2, and I took another vector V in quadrant 4. Let's add those together, and you'll see we're not in quadrants 2 or 4 anymore. U plus V is equal to 1, 1. Well, that's in quadrant 1. That's not in H, since 1 times 1 is not less than or equal to 0. So H is not a subspace of R2. Okay, so in this last example, we showed something was not a subspace, and that's pretty much the only way to do it. You have to find one of the axioms that's violated. To show a subset is a subspace, there's a quicker way than the way we did it in example C, where we use the definition. And that's using this theorem, theorem 1. If you have a set of vectors in a vector space, their span forms a subspace. So that's incredibly powerful theorem. We've got a proof at the end, but let's just see how that works. So I'm going to skip through this example. You can read this on your own. Subspaces in R3 are either lines going through the origin or planes going through the origin. But let's use the theorem to show that the set of vectors of this form is a subspace of R2. We could use the definition, but I'm going to show you this is a lot quicker to use theorem 1. So we're going to find two vectors that span H. So first of all, let me decompose vectors in H. A plus 2b, 2a minus 3b, we can write as the sum two vectors. A, 2a, plus, put our b's over here, 2b, negative 3b. Okay, let's pull an a out of the first vector, 1, 2, and let's pull a b out of the second vector. All right, a and b are any real numbers, so now we can see that H is the span of the vectors v1 and v2. So H is equal to the span of 1, 2, comma, 2, negative 3. That's the set of all linear combinations of those two vectors. And so by theorem 1, H indeed is a subspace of R2. Okay, here's another example, last one. H is the set of all quadratic polynomials that have nothing but a quadratic term. So there's no linear term. There can be a constant term. Since a is any real number, the 0 vector is in H. Let a be 0 and we get 0. And let's list some other vectors in H. Maybe t squared, negative t squared, 4t squared. Any constant times t squared will be in H. So how do we show H is a subspace of P2? Well, here's how we do it. H is equal to the span of the single vector t squared. In P2, vectors are polynomials, so it makes sense to say that. And so that does it. All right, so subspace recap. Quickest way to show a subset is a subspace is to use theorem 1. Try and find a set of vectors such that H is the span of those vectors. And the quickest way to show H is not a subspace, actually there's no quick way to do it. You actually have to find a vector or a scalar or a combination of vectors and scalars where one of the axioms is violated. And that is the end of this section.